Okay, in this video we're going to get into some notation, some tools that will be quite useful for your maths adventures further down the track. So hopefully we know that 5 times 5 is 25, but because we multiplied 2 copies of the same thing, we can write that as 5 with a little 2 there. We would say it's to the power of 2, or we'd call the 2 the index. There's all these names for it, but you'd probably remember that this is a special case, and we normally call this guy 5 square, because it actually counts the number of squares in a 5 by 5 grid. Or it's the area of a 5 by 5 square, same thing. So this means the same thing, it's just helpful to have this language when we do a lot of repeated multiplication like that later down the track. Another way to write this relationship is if we start from the other end, from the 25, we can reverse the square, so go backwards, by using what we call a square root, and that gives the 5. So it's like the square root of 25 is asking a question. It's asking for what positive number, when multiplied by itself, will arrive at 25. And 5 is the number that does the job. Similarly, if we do 2 times 2 times 2, we know the answer is 8, because 2 times 2 is 4, then double again gives 8. But because there were 3 copies of 2, we now have 2 to the power of 3, and the common name for that is 2 cubed, for similar reasons to the square thing. But again, it's just a convenient way to write the same number. We could go backwards from the 8 as well, by using a root, only this time there's a little 3 there, to mean we're asking for a number that arrives at 8 when you multiply 3 copies together, so that's going to be our 2, which we saw before. So, if we ask for what the square root of 49 is, for example, what you'd want to be thinking in your head is how do we arrive at the number 49? By multiplying 2 copies of the same thing together, and we're looking for a positive number that fits into those blue boxes. So if you sort of scan through your times tables, you might recognize that 7 does the job, because 7 times 7 is 49. So that would be our answer. Now, some roots, be warned, don't end up being very well behaved. Most don't end up being very well behaved. For example, root 20 here. Okay, if we put all our counting numbers in a huge line, okay, then think about squaring them. So think about multiplying 2 copies of that number together. We're looking for a blue number that when multiplied by itself arrives at 20. Okay, so let's start from the bottom. Of course, 1 times 1 is 1. Then 2 2s are 4, 3 3s are 9, 4 4s are 16, 5 5s are 25, but hang on, we were aiming for a green 20, and we've gone over. So that means the blue number we're looking for must be somewhere hiding in here. We have no idea what he is, and in fact, it's actually physically impossible to write down what he is as a decimal, which is kind of weird. But what we know for sure is he is somewhere between 4 and 5. So 4 point something something. Okay? Let's try one more. Let's say root 75. So we keep counting up our line. We were up to what? 6 6s being 36. 7 7s are 49. 8 8s are 64. 9 9s are 81. And again, we notice we've skipped right over the 75 we were aiming for. So square root 75 must be hiding somewhere in here. Again, we don't know where. Best we can say for now is it's somewhere between 8 and 9. Or we could whip out a calculator and get a decimal that's somewhat close to the real answer, but again, it is impossible to physically write out the whole decimal thing. So look, these numbers are sometimes kind of strange. Okay, but this is a way to at least know round about how big they are, kind of what numbers they're close to. So that's all for now. Thanks for watching. See you around.